The last intermolecular interaction we're going to see is actually the strongest type of interaction, and this is hydrogen bonding. So, hydrogen bonding is not an actual bond, so we're not talking about a bond between hydrogen and another atom. We're talking about an interaction here. So, it's not actually a bond, it's more an interaction. So, it's kind of unfortunate name that it's hydrogen bonding, but it's referring to an interaction. And it's a special type of dipole-dipole. So we saw dipole-dipole interactions in the first video and then the fleeting dipole-dipole in the second video. This one is also a special type of dipole-dipole. What we do need to have for hydrogen bonding is we do need to have a heteroatom. So that's an atom, any atom other than carbon or hydrogen. So we need to have a heteroatom with lone pairs and H connected to it in order to have hydrogen bonding. So we do have that here. Let's draw an example of this. So let's draw out those lone pairs on that oxygen. So what's happening here is that we do have this dipole. So we can draw in the dipole where the oxygen is pulling the electrons away from the hydrogen in that bond. So we can also put this as delta plus and delta minus with the oxygen. We also have lone pairs on that delta minus atom that can interact. And so what's going to happen if another molecule comes along? So say let's just say we have another molecule coming along with an oxygen and a hydrogen. What can happen is the oxygen with its lone pairs can start to interact with the H. So in this molecule, that H is also delta plus. Oxygen here, delta minus. We could also draw that same dipole. So the dipoles are aligning, just like we saw with dipole-dipole interactions, but we have this kind of enhanced feature where the lone pairs of the heteroatom are also interacting on a different level with the one of the atoms in the other molecule's bond. And so that is our hydrogen bonding. So we can have that when doing that. This oxygen can then go and interact with another a molecule's H, for example. So we have a pretty strong interaction because we don't only have this dipole-dipole and the dipoles aligning, but we also have those lone pairs coming in and also interacting with the hydrogen. So let's see what we have with more hydrogen bonding. The more hydrogen bonding that's possible, the higher melting point, boiling point, increased solubility in like solvents. So things that can hydrogen bond a lot tend to be more soluble in water because water can also H bond. And so anything that is able to also H bond, it'll be pretty soluble in. So in this question, we're kind of, so the other questions we were dealing with like boiling point. Now this question is asking which of these compounds do you expect to be more soluble in water and why? So what we're looking at, so water is H2O, and so it's able to H bond because of the structure. So with water, we have that same kind of thing with the oxygen and the hydrogen. We just have two of those bonds. And so what we're thinking about is, well, can these H's interact with, or how well can these H's interact with these molecules, and how well can these lone pairs interact with the molecules that we have? So in this one here, we have one OH group, so we can do H bonding with this group and water molecules. But with this one on the right, we actually have more H bonding possible because we have two OHs that can participate in H bonding with the water. So more H bonding possible for this one. And in this case, we're concerned with the H bonding going out to water and interacting with water, not so much interacting with each other, although it would also be able to interact together better if it was just for dealing with just that pure substance. So what this is going to do is water is going to be able to H bond with this molecule. and that's going to help these molecules become separated from each other because they can interact with each other. And as soon as water starts coming, it starts to disrupt those H bonds that this molecule has with other molecules of itself, basically. And so when that water comes in, starts to disrupt those, it's going to start to pull those molecules apart and start to dissolve that compound. And so this one's going to be more soluble in water. When we go down to look at the second example, we have an example of an ether. So this is an oxygen bound to two carbons, and we also have an alcohol, so ether versus alcohol. With this one, it's a little bit more tricky because so the H's of the water can interact with the oxygen, but this molecule doesn't have any H's that it can give back basically to the water. So it doesn't have any H's that can interact because it does have H's on the molecule, but they're not attached to the electronegative atom. They're attached to carbons only. And so this one can accept the H bonds from the water, but it can't donate the H bonds to water. So it can only accept the H bonds in the molecule on the right. We are able to accept the H bonds with the oxygen. So just put accept here. The H can donate H bonds as well. So this H can go and interact with the oxygen of water as well. So we just have more interactions on this molecule here. And so that one is going to be more soluble because we're going to be able to interact better with the water. And that's because it's an H bond donor and acceptor. And that means water can interact more strongly with this one. So if water can interact more strongly with this molecule, we're going to have more solubility in that water. And so that makes that molecule more soluble in water.